Okay, we are back. I hope you have time to try exercise 5. A bullet of mass 50 gram and electron of mass 9.1 and 10 minus 31 kg are both moving at 300 meters per second. Uncertainty of the speed measurement is 0.01%. If position and speed are measured at the same time, what's the accuracy that we can measure the position of each object? Right. So clearly this is a Heisenberg uncertainty principle kind of question. Right. So first we want to find uncertainty in momentum because I got speed, right? So the uncertainty in speed will lead to an uncertainty in momentum. So delta P equal to m times delta V. We want to find delta V, right? Delta V will be found by using this value. This is the percentage uncertainty. So delta V over V times 100 is 0.01%. And that's how you get delta V is 0.01 divided by 100 times V. And that's how you get this value over here, right? So m times delta V will give you this very small number. And then you substitute this into Heisenberg's uncertainty principle, which is delta x times delta P is greater than or equal to h. And therefore you get delta x is greater than this value over here. Okay, if you look at this measurement, this is actually a measurable distance, right? This is I think 2.4 cm. Yeah, this 2.4 cm, right? So 2.5 cm can measure, right? Yeah, so macroscopically, that means from our perspective, we can observe this kind of uncertainty in position, right? So the uncertainty in position of the electron is actually important in this case, or actually observable. Okay, for the bullet, right, I'll change the mass to the mass of the bullet, but this part is the same, right? Then I'll get this value. Then if I do the same calculation, I'll get this, right? If you look at this, this is absurdly small, right? Because atoms size is 10 to the power minus 10 meters. This is 10 to the power minus 31 meters. If I cannot even observe an atom, right? How can I ever observe this kind of number? It's not observable at all, all right? And that's why quantum theories don't really affect macroscopic objects, right? The numbers just don't, they're just not observable. It's not that they don't affect, but it's that they affect, but they affect in such a manner that the effect is not observable from our perspective, right? Which is why quantum is very non-intuitive to us, right? So this is why quantum mechanical principles are crucial for understanding working with microscopic particles, which I remind you again, involve photon, uh, subatomic particles, and atomic particles, right? That means anything to do with electron, proton, neutron, okay? Whereas classical mechanics suffice for most macroscopic objects in everyday experience, such as, in this case, the bullet, or for example, whether or not human beings exhibit interference pattern, right? Clearly, the answer is no. We discussed this problem earlier already. Okay, not going to go through it again. Right, move on next part. Particle in an infinitely deep potential well. Okay, this part is very theoretical. Okay, you're supposed to show an understanding of the standing wave solution psi n for a wave function of a particle in a one-dimensional infinite square well potential. Solve problems using En equal h square over 8ml square n square. Right, luckily this is given your formula sheet, you don't have to memorize, but I'll show you how to derive it later. Okay, for allowed energy levels of a particle of mass m in a one-dimensional infinite square well of width L. Right, so particle in infinitely deep potential well looks like that. This is an infinitely deep potential well. Right, basically this part here is of infinite potential. This part here is of infinite potential, and therefore the particle, right, say an electron, right, cannot exist at any value of x below 0, because if I exist here, my potential energy will be infinity, right? Or if I exist here, my potential energy will be infinity as well, which means not possible. And therefore, the particle must exist between 0 and L, right? But when a particle exists between 0 and L, the wave function, right, must tell me the probability of the particle existing between 0 and L. And the modulus of wave function square must sum to 1. Right, the area under graph of that modulus wave function square must sum to 1. Right, so that means the wave function must somehow cover the space from 0 to L. And then the area under graph of the modulus square of the wave function should give me the total probability of the finding the electron, which is 1. Alright, so I need a wave function to represent the particle from 0 to L. Right, and also can I exist at 0 and L? The answer is no, right? Because if I'm at 0 and L, my potential energy is also infinity. So I know that the wave function must give me 0 at 0 and L. But in the rest of the space in between, I have to figure it out. And how this wave function actually exists is that the wave function is actually a standing wave. All right, you don't have to know too much about this. I just tell you some of the limitations, some of the ideas behind why this is so. So these are the wave functions of a particle that are possible at different energy levels, right? So the n represents, you can think of it as different energy levels, right? Actually, n is the quantum number, right? So a wave function of electron can exist like that, can exist like that, can exist like that, right? What's key is that you observe that at 0 and L, they are always 0. Because if the particle exists there, the energy is infinity, not possible, alright? And then everywhere in between, it's possible to get another 0 lah. For example, in this case, there's no other 0. In this case, there's one more 0. In this case, there's two more 0. How you realize that this is very similar to the harmonics in your standing wave, in your standing wave that you learn in superposition, classical superposition, right? So the chapter on superposition in classical physics, right? That this is your simplest harmonic, your first harmonic, your second harmonic, your third harmonic, right? And what's interesting is that you can see that this one got 2 notes, right? This one got 3 notes, and this one got 4 notes, right? So what this tells me is that if it were this wave function, the electron can be found anywhere. Most likely it's found at the center, because if I modulus square this function, I will get the probability distribution function, right? But if I were in this state, I cannot find the electron here, right? It's actually 50-50 between this state and this state, all right? And then of course this one the same thing. I cannot find the electron here and here, but I can find it within here, and within here, right? So that's the idea behind standing waves, all right? To represent a particle in an infinitely deep potential well. Right? Yeah, so that understanding of standing wave solutions, right? So the standing wave solution, right, generally in the question, they will try to help you a bit. But normally if you look at this, what do you think this, how does the equation describe this wave function? Should be a sine wave, right? You can see, right? This is like half a sine wave. This is like a full sine wave. Okay, a full sine wave with wavelength here. Okay, then this is 1.5 wavelength, right? So that's the possible ways to represent the stationary waves in this wave function. All right. So what we're going to do is that we're going to try to derive the amplitude and the omega of this wave function against x graph. Right. So for infinite well, the possible wave functions of electrons for an electron are drawn as stationary waves as shown in the above right graph. This one is here. Okay. This one you must be able to draw in exam. Okay. Let the general waveform of the wave function be psi equal to a sine bx, right? A is the amplitude of the wave function, which theoretically has no meaning. We might remember the front part we talked about wave function, right? But it does represent the amplitude of the wave, okay? Amplitude of the wave function, okay? Then sine bx, right? B, this B here is something like omega that you learn in your simple harmonic motion or in your wave, right? Not very dissimilar from the omega, okay? So at boundary condition, right, at x equals 0, right, recall we said that wave function must be 0 because the electron cannot be found here, because if it's found here, it has infinite energy, right? So not possible for the electron to be found here. Therefore, wave function must be 0 at x equals 0. So I do a substitution here. When psi is 0, x is 0, right, then I'll just get, okay, it looks like it fits this equation, right? So this condition seems to fill the equation well, right? But doesn't really tell us anything. But at the L, right? So at L, again, the same condition must apply. At x equal L, wave function must be 0 because again, I cannot find the electron here. Let's say I'm talking about electron. Then the wave function must be 0 because I modular square this thing must still be 0. The only way to be 0 is if wave function is 0. So I do a substitution of wave function is 0 here, right? And x is L, right? Then I try to find what are the possible values to satisfy x equal L and phi psi equals 0. So the possible values of BL are BL equal 0. Because BL equals 0, sine 0 equals 0, can, right? So or BL equal pi, right? If sine pi, you get 0, right? So again, a sine 0 will be 0, right? 2 pi, sine 2 pi, again 0, right? So all, BL can be any of these numbers, right? BL can be any n pi. Right, so when we observe this trend, right, we should be able to get the general formula that Bn is equal to n pi divided by L. Alright, so this is the general formula that we can derive from our observation, right? And therefore, we can generalize the equation to become wave function of n equals to a sine n pi x over L. Okay, can? Alright, so this is the general equation for the wave function that is observed here. Alright, then if we look at then we move on, right? So after we find the general equation already, we'll try and find the amplitude, right? So how to find amplitude? Remember that total area on the graph must be 1 of the psi square, the modulus psi square graph, alright? So if I look at the graphs of all these three, I try to square them. So I square this one, I'll get this one, right? Remember that this curvature changes, it doesn't become more and more steep here. It tends to 0, alright? So when I square this one, I get this one. When I square n equal 2, I get this one. And when I square n equal 3, I get this one. Okay? Then I try to make sure the area on the graph is equal to 1 to find A. So what I do is the same thing. This is similar again to your RMS idea in your AC current, right? You remember that you have to cut the area to fill here so that this become a rectangle, right? So the area of this rectangle given by a square over 2 multiplied by L must be equal to 1 because this whole area must sum to 1. So if I cut this area, which is the same as this area, and I cut this area, which is the same as this area, and bring it down, it becomes a rectangle like that. And this rectangle, the area must be 1. So a square over 2 times L must be equal to 1. Right, so a square over 2 times L equal 1. So a must be square root of 2L. And therefore, I have discovered the amplitude for this wave function. Right, and therefore, I have gotten the whole wave function. So the wave function n, right, because n represents, it can vary depending on the quantum number n, right, is square root 2 over L sine open bracket n pi x divided by L. Alright, so this is the general equation, right? And therefore we have sort of found this. Right, show an understanding of standing wave solution for a wave function of a particle in a one-dimensional infinite square well. Right, so in exams, what they can do is they can ask you to find A, or they can ask you to find the B. Right? Okay. Right, so we'll look at this exercise quickly. Right, you can pause and do it, then I'll cover the example and we'll close this part. Okay, we are back. I hope you have time to try question exercise 3. Okay, this graph is the wave function of electron, how it varies with position inside infinite square well with boundary x equal minus a and x equal a. Find the amplitude of the wave function in terms of a. Right, first thing I need to do is find the wave function. Right, so rather find the wave function square. So I need to draw the wave function square to look like that. Right, so a become what? A square. Right, but this is minus a and this is a. Right, and the area under graph here is equal to 1. So a square multiplied by this, right? So this is a square multiplied by this, 2a is equal to 1, right? Then what is a? A will be square root 1 over 2a, right? So I think my answer got some issue. Sorry. So this answer should be wrong. It will be square root 1 over 2a. Okay, I'll make the amendment in your notes. All right, so don't worry about that. All right, so with that, I'll end this part of the lecture.